Yeah, okay. So we're going to have the very last session of our wonderful Zoom workshop. And the first speaker in the uh, session is Diego Mejia of Shizuoka University. And he's talking about preserving failures of simple fragments of Martin's axiom. So please.
Okay, thank you very much. Am I loud enough? Can you hear me well?
Yes, yes, I think we can hear you very good.
Okay, thank you. Okay, so I want to thank Jörg Blendle and Professor Jörg Blendle and Professor Hiroshi Sakai for letting me join this workshop on the occasion of Sakai Fuchino's retirement. It's for me, it's an honor to participate in this conference. Also because, well, I'm very grateful also with Professor Sakai Fuchino for a lot of assistance that I got from him when I was doing my PhD in Kobe. And well, I want to wish Professor Fuchino a very nice, nice days in the retirement, like full of mathematics, that you can enjoy a lot of mathematics and also, of course, many other things. Okay, I'm happy that also Professor Fuchino in his talk, he mentioned things about Martin's axiom, because then this talk will not be that disconnected from what Professor Fuchino was talking about. So I'm going to talk about preserving failures of fragments of Martin axioms, preserving like some type of simple failures. This is a joint work with Martin Gorstern, Jakob Scherner, and Saharon Shelach. This forms parts of a series of works when we have developed forcing techniques to separate many cardinal characteristics of the continuum. So like the first big result in this direction was Goldstern, Kerner, and Shelach's Chiho's maximum, when they separated the cardinals in Chiho's diagram in 10 different values, which is the maximum number of possible values. Then after that, I joined them and started researching in this direction to separate more stuff simultaneously. And well, when we included numbers related to Martin's axiom, then some like nice, interesting results came up. Okay, so just to give a little bit of background, so let's introduce how these type of Martin's axioms are stated, or these are like more generally thought as forcing axioms. So let's fix a poset, forcing notion. So just a simple notation, dense P denotes the collection of dense subsets of P. And when we have a collection of dense sets D, we say that a filter is PD generic if the filter intersects every dense set from D. So, well, usually instead of a class of dense sets, it is usually mentioned models in this part, like PM generic, meaning that you are generic over M in some sense. But here I'm just, yeah, since I'm going to focus on this type of axioms, I will just focus on family of dense sets, right? So that's why I use this notation. So now, if C is a class of posets and kappa is an infinite cardinal, then we can define the following instance of Martin's axiom, which is Martin's axioms kappa on the class C. And this means that whenever you have a poset in the class C and a collection of dense sets, well, at most kappa many dense sets, then you can always find a PD generic filter, meaning that you can always find a filter on P intersecting every dense set from D. Okay, so you can always diagonalize in some sense at most kappa many dense subsets of every poset on this class C. So just to mention some folklore examples, things that everybody knows when starting to study these things, that, well, when kappa is Aleph 0, well, Martin's axioms always holds. In this sense, you can always diagonalize a countable family of dense sets in any poset. But in the case of Cohen, it can fail when you try to diagonalize continuum many dense sets, because, well, in that case, it's like you are producing a new real as well. So that's why it fails. So I will go a little, I will say a little bit more about this later. So now, well, I'm just repeating here the axiom, the MA kappa C axiom. So I'm focusing on failures of the axiom. So if P is a poset and D is a collection of dense subsets of this poset, then we say that the pair PD fails Martin's axiom if there is no PD generic filter, if we cannot find a filter diagonalizing this family of dense sets. And even more if the forcing belongs to some class that we fixed from the start. We in particular says that PD fails Martin's axiom on the class C, when restricted on C. Okay, so when I mean failures, I mean pairs in this sense, like a forcing and a collection of dense sets that cannot be diagonalized. And this motivates, well, or the failures are represented by this cardinal characteristic. So for a class C, we define MC as the minimum size of a collection of dense sets such that there is some, well, as of course this depends on some forcing, but it's the less amount of dense sets of some forcing that fails Martin's axiom for this class C. Or well, or saying in another way, this is the smallest kappa such that the axiom MA kappa C fails, right? But the point here, I express it as failures because, well, this number here, this MC, is witnessed by a failure, by a collection of dense sets on some P. So that's why, since, well, the notation of this talk is given in this direction, then I will talk a lot about pairs of failures. So just looking at simple properties of these numbers, if we have two classes, C and a larger class C prime for posets, then we're taking these Martin numbers, to say it in some way, then the number for C prime is below the number for C. Well, the reason is that, well, if you have a failure on C, then this is obviously a failure on C prime. So we have like these inequalities. And well, as mentioned before, well, for everything, we can always diagonalize countably many things, but you can find easily a poset where you cannot diagonalize LF1 many sets. So this is, for example, if you try to add an onto function from omega into omega 1. This is a failure of size LF1 of the Martin's axiom on the class of all posets. So you can say, well, from here that by the property 1, then you can have, well, that MC is always uncountable. And well, I'm coming back just to coenforcing. If we look at the Martin number for the coenforcing, this is the same as considering all countable posets. And well, the number that characterizes this is the covering of meager, right? You can always diagonalize collection of dense sets in coenforcing if they have size smaller than the covering of meager. But if you have a covering of the meager sets, then you cannot diagonalize that, because, well, this means that you will have like some real avoiding all these meager sets when they are supposed to cover all the reals. Okay. So now the objective of this talk, as the title mentions, is to preserve failures. So I want like to produce some failures PD of some instance of Martin's axiom, and then preserve it in forcing extensions. So the effect on this on the cardinal invariants is that, well, this means that we are going to preserve like some equality like this in a forcing extension, some upper bounds for the number MC. So the focus of this talk is in this direction. But we are not going to look up sophisticated things like the class of all the proper posets, for example, but we are going to look at simple things, like very simple things like CCC, or strengthenings like K-Gnaster or Precaliber. Everything around CCC, nothing sophisticated will happen. So a very typical example of preserving failures is the following. we know that Suslin tree is a very bad failure for Martin's axiom for CCC posets, right? If we have a Suslin tree, we know that Suslin tree doesn't, all the anti-chains are countable, so T is CCC, and you cannot find an uncountable branch in T. Well, that's that forms part of the definition of a Suslin tree. So then this is witnessed by this dense subset. So if you take the alpha as the set of nodes of level above alpha, they form a dense set. And well, and this density, this Aleph1 many dense sets witness that T fails. That T fails the Martin's axiom for CCC. And well, and how about preserving it? This is related to the following property. If you make a product of a CCC poset with a Naster poset, you get a CCC poset again. So in other words, what this is saying is that Naster posets preserve CCC posets, in particular, it preserves Suslin trees. So Naster posets preserves a failure of Martin's axiom for CCC, in particular, well, a failure of size Aleph1, which is particularly a Suslin tree. So this is a simple example, and we are going to make like similar discussion in a wider sense. Okay, so I want to introduce the classes of posets like in the context, like K-Naster, Precaliber, etc. So I'm going to do this in a very general way with a formal approach, with the following formal approach. So I'm going to look at properties of subsets of posets and calling this gamma. Like if you want to interpret it in more formally, well, gamma is a function from the classes of posets such that, well, gamma P is a collection of subsets of P. So this is like a point class. I mean, when you think about Polish spaces or in descriptive set theory, you talk a lot about point classes. So this is like point classes in forcing notions. So typical examples are, well, when we talk about n-linked subsets, I will denote this point class by lambda sub n, the point class of n-linked subsets. So this is interpreted in the following way. So lambda n of P will be the following. So a subset of P's in lambda n of P is n-linked if and only if, well, any subset of A that has at most n elements has a lower bound in P. Okay, the lower bound doesn't necessarily have to be inside A, but it is just in the space in P. So this typical property of being n-linked is like a point class for posets. And also, well, the known centered property, which I will denote by lambda less than omega, which is somehow like the intersection or well, since these are properties like the infinite conjunction of the lambda n's. This gives the center subsets. Well, obviously, if you make the intersection of the delta n p's, which is actually this thing, so a set A is there if and only if it's centered, and well, this means that any finite subset of A has a lower bound in the space in P. Again, not necessarily inside A, but outside. It could be outside, but it's inside the space in P. So use the typical examples. So now from a general property gamma like this, I want to define the following properties of forcing notions. So given a cardinal mu, we say that a poset P is mu gamma covered if it can be covered by at most mu many subsets of gamma P. Okay, so that's why like you can cover it by at most mu things. This is a number, a name I came up with. Perhaps I'm sure there could be a better name. But okay, but I'm very bad I'm very bad at choosing names, and you will realize this later when you see a lot of notation that I put in that are like very weird names, and this is one of them, mu gamma cover. So you can cover by mu things on this from the space gamma, and we have like a generalization of Naster property with respect to some property gamma. So we say that a poset is mu gamma Naster if any subset of P of size mu contains a set of the same size which lies in gamma p, or which has property gamma. So if you think about the Naster property or the precaliber kappa for some cardinal kappa, so actually this falls into like this formalism. Like you can find a point class, you have a point class where you can define this. So this is in some sense like practical to express things. And for some other stuff, I will tell in a bit. So I'm interested on this just because this formalizes things that we already know. So if we look at examples like lambda n, so mu lambda n covered for some natural number n, above 2, just means mu n linked. And this just means that, your deposit can be covered by at most mu many n linked subsets. This is a typical notion. And and the Naster property, gives you like what you know as the Naster property. Like for lambda n gives you theta n Naster. So meaning that for any subset of the forcing of size theta, you can find an n-linked subset of the same size. So in particular, the Naster property that we all know is Aleph1 to Naster. Okay. For any uncountable subset of the poset, you can find an uncountable linked subset, a two-linked subset. And when we look at lambda less than gamma, mu lambda less than gamma cover is the property mu centered. You can cover by at most mu many centered subsets. And and the notion sigma center means that you can cover by Aleph 0 many center subsets. And and the Naster property for this lambda less than omega is precaliber theta. For any subset of size theta, you can find a center subset of the same size. So now, for a very curious example, let's look at gamma 0 as the following property. So let's say that a subset A of P has property gamma 0 if and only if either A is, has size at most 1, or it is not an anti-chain. So why this? So if we look at the properties of forcing notions, so what will mean mu gamma 0 covered? In this sense, it means that I can cover P like either with points or with things that are not anti-chains. But if I have something that is not an anti-chain as a cover, then P itself is not an anti-chain. So it's like P itself is like a covering of itself in this class. But if it's only covered by points, then what we are saying is that P has just size less than equal than mu. So is this disjunction, like P is small or P is not anti-chain, which is not interesting. This is actually not interesting at all. But the following property is interesting, theta gamma 0 Naster, which means, if you make the calculations in your head, you'll get that this is actually theta CC. So we can characterize theta CC as a Naster property for this very curious point class. So considering further properties, typically we know that, for example, for link, that mu linked implies mu plus Naster. In point classes, this can be generalized very easily when gamma is downwards closed, meaning that if you have a set with property gamma, then all its subsets also have property gamma. But there are counterexamples like this gamma 0, right? Gamma 0 is obviously a counterexample of this implication of how you can get from cover to Naster. But it still is nice because, I somehow personally like this. Because of the following generalization. So we know that, finite super iterations of CCC posets give you CCC posets, and also of Naster posets gives you Naster posets, or for precaliber Aleph1 gives you precaliber Aleph1, and so on. But actually, this is some property that actually can depend on the point class. And this is some work I did some time ago. So if we have that mu is an infinite cardinal, typo here, sorry. And if theta is uncountable regular, then you have the following. So we can determine properties on gamma for the following situations, for each of the following situations. So if we think about finite support products of theta gamma Naster, so we can determine properties of the point class such that always finite support products of theta gamma Naster posets is again theta gamma Naster. And also for finite support iterations of the same type of posets. So we have, yeah, I somehow like defined some properties like determining this. And this can even be extended to the property mu gamma covered. But of course, the restriction here is that the size of the product of the iteration cannot be too high. Well, too high. So the size must be bounded by 2 to the mu. Okay. Which is, well, as you know, that if you make the I don't know, if you make the finite support product of co-enforcing, but if this is too big, then it's not sigma linked anymore. It's like this type of thing. So this appears in a paper whose main results is about something like very different matrix iterations with metrical support restrictions. And well, the name of the section says everything, bonus track, because it's, well, not the main point of the work, but it was something interesting that happened that, well, just appeared because of some like point class that I defined that characterizes, well, not characterizes, but implies that you don't have dominating reals. So because of the discovering of this point class, then I was like inspired to do like this formalization. So in particular, these 2 point classes, lambda n and lambda less than omega, well, and linked and centered, they fall into these 2 properties. So in some, you have like here in a single proof that the iteration of Naster posets is Naster, like, and for, well, and all of these variations. Yeah, so all these properties are known, of course. But, well, I gave this formalization, and, well, the formalization is not that far away from the original proofs. And of course, well, gamma 0 only satisfies, well, the second property. But we know this because, well, gamma 0 is associated with CCC or kappa CC. They don't respect finite support products in general, but they respect finite support iterations. So it's like enclosing everything in a single formalism. Okay. So just after this digression, I just come back to Martin numbers again. Okay, so easy properties. If a property gamma implies a property gamma dash, then of course the mu gamma covered posets argue mu gamma dash covered. So when you compare the Martin's numbers, well, the Martin number associated to the gamma with the gamma dash is below the other one. And the same for the Naster properties. So the Naster from gamma implies the Naster from gamma dash, and then the relation of the Martin numbers are, well, the converse. Now, well, just to fix notation, well, the notation that everybody knows. So when you have Aleph1 in Naster, well, Aleph1 is typically suppressed, and you just say n Naster. This is when n is, well, the correct notation is when n is above 2. But I will abuse notation and sometimes talk about one Naster. In this sense, one Naster will just mean CCC. So this is a very, I will say, bad abuse of notation, but this is just for practicality in the notation. And I will do the same with precaliber Aleph1. So when I say omega Naster, I mean precaliber Aleph1. And this is just, well, to put all these Martin numbers in the same definition. So m gamma just means m gamma of the Naster, m of the Naster property when gamma is bounded, is between 1 and omega. So, well, so for example, m1 is m of CCC, and m of omega is the m of precaliber Aleph1. We apologize for this abuse of notation. And, well, and about linked, well, sigma n linked is, well, what means Aleph 0 n linked, that you can cover with comfortably many n linked subsets. And, well, and when n is equal to 2, n is usually suppressed, so you say sigma linked. Okay. So now, well, things that you may already know, that most people know. So from the relation of these point classes, well, the implications are in this, is like this diagram. So then this gives the implications of the Naster and the covering properties or the linked or center or precaliber, etc. And then when you take the Martin numbers, then well, the relations are inverted. So when you look at M1, M2, M3, well, this is increasing up to M omega, and the same for M sigma 2 linked, M sigma 3 linked, and all of them are bounded by M sigma centered. And M sigma centered, we all know that this is P, and now we know that P is equal to T. So okay, so they are the same cardinal characteristic. For this talk, I'm not going to say much about the sigma link properties, but I will center on this part below on M1, M2, M3, etc. And also we'll talk about P. So it's about like this lower chain and with this bound P. So, okay, before continuing, I will just mention some curious facts associated with these numbers. So there is this result, which is some generalization we obtained from folklore results from Kuhnen, Raubadan, and Solovey. So assume that C is a subclass of CCC and that is closed on their countable finite support products. Well, finite support products of countable size and closed on their cones, meaning that if you restrict if you have a forcing in C and if you restrict the forcing to some condition, then this is again in C. For example, Naster is like this, or N-Naster is a class like this. Even the sigma N link, the precaliber and sigma center is like this. CCC, not in general. Well, it depends on which theory you are. But then if we assume that the Martin of C is larger than Aleph1 and takes some value lambda, then we have the following property. We have that for every poset in C and for every subset of P of size less than lambda, you can always cover A by countable union of sets of center subsets of P. So of course, this doesn't mean sigma centered, okay? So this is actually weaker because the lower bound of the covering is not found, well, or the lower bound for pinks are not found inside A, but inside the larger P. So this is weaker than sigma center, but is, well, some practical notion that you can always cover small things by countable unions of center subsets. And this somewhat, well, the implication I'm interested in is the following one, that C is containing precaliber Aleph1. So what this generalizes is just, well, I guess this is what follows, right? That, well, it's associated to what follows. So for example, if you look at Martin of on CCC, if Martin of CCC is larger than Aleph1, or mean that MA Aleph1 on CCC holds, then this implies that products of CCC posets are CCC. So this means that CCC satisfies the properties of this fact, and therefore this means that CCC is equal to precaliber Aleph1. This is what it's saying, that CCC and precaliber Aleph1 are the same properties, and this is reflected in the Martin numbers. But since kappa Naster also satisfies this, then in general what we have is that for any natural number k, if mk is larger than Aleph1, then mk has to be an omega. Okay. So this means that in the following diagram, if you look at the lower part, if one of the m kappas is larger than Aleph1, then all of them starting from there will be larger than Aleph1 too. So this actually says that, well, when you look at the m gamma numbers, you only have at most two values. Like either all of them are the same, or they can only be separated into two different sections. Okay. So this means that, yeah, we cannot separate, for example, this m gamma into infinitely many things, like not into three. So now I will just fix some playground about this, like just the motivation of the results I wanted to present today about the preservation of these failures. And well, and is the following theorem, which you may notice is like, well, trying to force that any possible separation of, or well, any possible cut of these mk numbers is possible, that they can be realized. So this was known long ago, I think by Todorcevic. But here we wanted to put more stuff. Okay, so on one hand, when we cut this thing in two, we can cut at any k that we want. So if we choose some k, then everything below k or indexed below k is aleph1. We can force it aleph1 and force that everything from k is lambda. For some lambda, that can be any arbitrary regular cardinal. So we achieve this on one hand, and on the other hand, we can, in addition, like force more stuff. Like we can attach this to Chihon's maximum, so like forcing Chihon's maximum while forcing this thing about the Martin's numbers, and also separate P in addition. And we can do this as long P is forced below the additivity of null. Okay. We don't know how to do this if we consider like larger values, but at least, well, we can separate many under these conditions. So now, okay, towards this motivation, then I will just explain what type of iteration is doing this. And from there, I will explain like which type of results we're looking for. So then, like, thinking about just Chihon's maximum or in the simple context, okay, if we want to separate all diagrams, all cardinals in Chihon's diagram, then we start adding many cohen-reals. We add a lot of cohen-reals, and actually, well, as many as the value we want to force for the continuum. So this is just to add a lot of witnesses of things. They are cohen-reals, and then after that, we use, I don't know, fragments of random forcing, Heckel forcing, and things like to modify the cardinals in Chihon's diagram. And well, the common property is that all of those posets will have is that there will be sigma n linked for every n. Okay, and this is even true if we want to include P, because well, to include P, you just have to insert sigma-centered posets in your iteration. So just to put it into simple terms, we are just going to be looking at iterations of posets that are sigma n linked for every n. That's like all in this context. You can forget about Chihon's maximum and the other things. We are just looking at an iteration of this type of posets. But of course, we have to plug in more stuff depending on what we want to force about the Martin numbers. So depending on the case, depending on each K, we have to do something different. And well, I will center in each of the cases. About P, well, P will be mentioned at the end of the talk, like why we can force it, like, yeah, between M and the additivity of null. And well, and just to note, if we look at, well, the numbers, most of the numbers are below the additivity of N. Well, the sigma and link numbers are below the additivity of N. But M omega, the one for precaliber, they could be even larger than the covering of N. So this way, like, violates this rule. So this means that there are more possibilities for these numbers than we are looking at in this result. Okay, so let's get started. So of course, here I'm allowing to make everything constant equal to aleph1. Okay, so this is something that is known. So to force that all these numbers, in particular that M omega is aleph1, well, the iteration itself does that. Because of the following, so this is known. So by Devlin and Shelah, we know that, well, M omega larger than aleph1 implies that any ladder system coloring can be uniformalized. So I apologize, I'm not going to explain this. So, but in other words, it means that, well, looking at the contrapositive, any ladder system that coloring that cannot be uniformalized represents a failure of MA precaliber. And it's a failure of size aleph1 particular, like ladder system colorings are like in the context of omega 1 as well. And well, and we note from Barnett that after adding a cohen-real, there is a ladder system coloring that cannot be uniformalized, even when we follow it by sigma-linked forcing extensions. So now in the context I described before, So we first added a lot of real using coin reals. In particular, there is this one coin real adding the ladder system coloring that cannot be uniformalized. But then this is followed by many sigma link posets. But since we already made the continuum too big, of course, the length of the remaining part of the iteration is not that big. So it is still, I mean, everything will be sigma linked after the coin things. So model of the coin things. So then this is what justifies that in the iteration described before, we can force the failure of recalibrate at Aleph1. So now, okay, from now on, let's avoid these trivial cases and assume that lambda is larger than Aleph1. And first look at the case when we cut on some finite k. Okay, meaning that we want to make mk large, mk equals to lambda, and well, and from there below, like mk minus 1, I want that to be Aleph1. So then in this case, now because we want to force that mk is lambda, so then we have to insert more stuff in the iteration. It's not just this sigma and linked for all n, but we have to diagonal, well, yeah, add generics for Kappa-Naster posets, small Kappa-Naster posets. So then we have to, like by bookkeeping or counting arguments, we have to insert all the possible k-Naster posets of size less than lambda in the iteration. And this is to force that mk is large, that mk is above lambda. So this guarantees the lower bound of this, but now we have to guarantee upper bounds. So then we need to ensure that mk actually becomes lambda, and that everything below is Aleph1. And of course, this is in the case when k is larger than 1. So then the strategy here, well, we look at what type of iterants we have. We have that all iterants are sigma and linked for all n. So in particular, some of them are like that, and there are the small nasters. So they are either k-naster, all of them are either k-naster or are lambda n naster. Okay. So the sigma n linked will imply this lambda n naster, obviously. And these k-naster things, new k-naster things that we added, since they have a small size less than lambda, then anything that is small satisfies the lambda n property for any n. So we have that the iterants, or in particular the whole iteration, has these two properties for and the second one for any n larger than kappa. Well, any n between any n between k and omega. So therefore, like for the first line, if we want to ensure that mk is below lambda, then we have to ensure then that lambda k plus 1 naster posets will preserve mk small. So this will become like the mission, like the target that we would like to see. Okay, this on one hand. So this ensures item 1, but how about item 2 of forcing that the other values are Aleph1? Well, this is by applying somehow the same result, but instead of lambda considering Aleph1. So since the iteration is Aleph1 k naster, then this should preserve that the value with the index k minus 1 has to be bounded by Aleph1, by this thing from the property. So this is what we are going to look at. Okay, so in this context, so this is known by Todorcevic, at least for the case lambda equals wait a second. Sorry. So this is known by Todorcevic. We just like updated the notation of what this means. So let's look at the following type of sets. So we look at the space n to the omega, so functions from omega into n when n is above 3. And we say that a subset of reals there is less than n array. This is, well, the original Todorcevic definition. I prefer to call it an hour dense plus. I warned you about the bad names, right? And it means the following property. So it means that for any finite sequence of numbers in N, I should draw a picture here. So if S is any sequence, then we can always extend it by just one point I, such that when we look at all the reals extending S attached with I, then all these things here, this is S attached I, well, the set of reals that extend this, all the things of this tree, well, nothing from X will fall inside this set. So this is what we have. So that's why I call it a Nauer dense plus. So because it's like Nauer dense, but you don't have to go too far in order to avoid X, but you just go one step to avoid it. So it's just a name that allows me to remember what is going on. So this is Nauer dense plus. And well, as we can talk about losing type of sets in this context. So if set is a set of reals in n to the omegas, and then we say that the set is lambda losing plus, if it's large, if its size is above lambda, and if set doesn't contain Nauer dense plus subsets of size lambda, meaning that all the Nauer dense plus subsets that set contains have to be small, have to have size less than lambda. So yeah, it's like a reformulation of losing body in this context. And well, and such sets are defined a positive in the following sense. So for any set, so just wait me a second. It was just getting too dark here. So Q set is composed by conditions that are finite partial functions from set into omega, I mean with domains on finite U, such that the inverse image of any point is Nauer dense plus, and this for any n less than omega. So we look at this type of functions, and this is ordered by, well, like larger things, okay, increasing the function in this sense. So what does this do? So this forcing will add you the following. So it adds a map from set into omega such that the inverse image of n for any n is Nauer dense plus. So this means that in general, this Q set is adding a large Nauer dense plus set, meaning a Nauer dense plus set of size, subset of size lambda. So somehow what we are saying is that we are destroying the property lambda losing plus on the set. And this is what is described in the theorem. So if set is lambda losing plus, then the forcing we described fails Martin's axiom. Okay, so because we cannot destroy the losing property for set, and we can and it can be shown that this Q set is n-1 Nuster. And is witnessed well by these following dense sets, which is as expected. So even more, if lambda is less than the continuum, then, well, actually this set becomes sigma n-1 linked. Okay. So okay. So this is like, I think, a reformulation of Torovsevic's result. So it means that, well, if we want to force or if we have to have a failure of Martin's axiom of n-1 Nuster, then all we have to do is produce a lambda losing plus set. This is like the message here. So also this is not like in the case of normal losing sets, after lambda many coin reals, you can add, well, typo here, this is lambda losing plus subsets are added after lambda many coin reals. And also, on the other hand, we have coin reals at this type of sets, and they are preserved by lambda and master posets. So then this can be applied to the previous iteration we talked about in order to make the separation we want. So when k is above 2, then we can guarantee that mk is bounded by lambda. So this is by the theorem here, because well, the first coins give us like the losing plus set we want, and well, when applying this to n equals k plus 1, then we are preserving this thing small. We are preserving the losing plus set. And even more, if k is a bit larger than 3, then we can apply the same theorem, but to lambda equals aleph 1, so that we can force, as well mentioned before, that mk minus 1 is aleph 1. So this is just by the same theorem applied to n equals k, and with lambda aleph 1. So there are some trivial cases here too that I didn't mention. I will just quickly review them. So if in the case k equals 2, then we haven't said why we have m1 equals aleph 1, but this is thanks to Suslin trees, because well, the iteration is to Naster, and we mentioned at the beginning that to Naster preserves Suslin trees, and well, it is known that you can add a Suslin tree by adding a coin real. So since we are starting with many coin reals, then we have a Suslin tree there that is preserved up to the end. And well, and finally, well, the case k equals 1, the remaining somehow like, let's call it trivial case. So this means that we want to force everything to be lambda, m1 equals lambda. But of course, well, we are increasing m1 from the beginning, adding a lot of CCC posets. So we just have to think about finding an upper bound for m1. But since m1 is m omega and is any mn, we just have to bound one of them. But this again is followed by Todorsevic's theorem. We can just preserve some larger failure. That will be all in this sense. Okay. Now, for the high case, I didn't discuss the case k equals omega. And well, this means that we want to force that m omega is large, that the precaliber number is large, but the other Naster numbers are aleph 1. So this is the remaining case of what I was discussing on this theorem. And well, and this is where our original results lie. Okay, naturally, well, for the case k omega, so of course, as I reviewed that we had a sigma n linked for all n in the iteration, but now to force some value on m omega, well, to force it equal to lambda, so the step is to insert in the iteration by bookkeeping precaliber aleph 1 posets of size less than lambda. So this is in order to increase m omega above lambda. So this is, well, done by the usual techniques. So now we have to force that, well, the upper bound, okay, that m omega actually becomes lambda. So now we have to look at the properties of the iteration. So as mentioned, it is formed by a lot of sigma n linked posets for all n. So they become n Naster for all n because, well, the new things we added are precaliber. But they are small, so they become lambda to Naster. Okay, so the forcing has these two properties, n Naster for all n and lambda to Naster. So now, then being a Naster solves one of the problems by previous Todorsevic's theorem, because then this ensures that all of mn's will be aleph 1, meaning that we are going to preserve all these Naster failures. So then what remains is to force m omega equals lambda. So then the challenge here, as observing here, since the n Naster property is used to have mn aleph 1, then the lambda to Naster property will be used to preserve a failure of precaliber aleph 1. And this is the direction of the main result. So now what will we do for this? So we wanted to add coloring using a coloring that somehow witnesses this failure, as we have, well, this failure of precaliber aleph 1 of precaliber omega 1 for lambda equals aleph 1 that we discussed before. But now this is extended to lambda when lambda is larger than aleph 1. So then we want to add a coloring that gives us this witness. So this coloring will have many properties, but then I will explain how they are motivated. So we have that we say that a pair C D bar is a lambda type coloring. Again, this name is not in the paper, it's just something I came up for this talk. I apologize. So this means that, well, C, the main thing is that C is a coloring of subsets of lambda of size 2, and we just color into 2, into 0 or 1. We just give 2 colors. I will explain what the bars do. But okay, but the point is that from the coloring, we want to look at the forcing of homogeneous sets, well, homogeneous of value 1, right? So we look at the finite subsets of lambda such that the coloring on this restricted to this set is always 1. And again, ordered by a superset, as usual. I think this is very usual in this context of coloring, adding things, and I don't know, like large homogeneous sets, something. So then, okay, we want that this is a failure of precaliber omega 1. So in order this to be a failure, well, first, what does this forcing do? Well, so first, well, we have to, we look, or well, we want this to add a large homogeneous set, a large one homogeneous set, in this case, well, of size lambda. So then we insert a property to have that. So very simple properties just, well, for any finite subset of lambda. Well, we look at the ordinals such that the coloring of psi eta is 1 for any object in U, for any psi in U. Meaning that, well, if we want to, if we have that U is or to say in other words, if we have that U is one homogeneous, then we want to like add 1 point, and we want to add it as far as we can. So then these properties ensure this, because this set is saying that, okay, these etas are like the good etas, the etas that allows to increase U as a one homogeneous set. And we just want that there are many of them, that they are unbounded, many of them, in order that we can always like increase as much as we want. And then at the end, this forcing will add one homogeneous set of size lambda. So this is ensured by property 2. And we want that this is a fail. We want this to be a failure of precaliber aleph 1. So to be a failure, we want that this homogeneous set is not in the ground model, okay? Meaning that we cannot have this homogeneous set. And this is witnessed by the property number 3. Property number 3 says if we have a pair with this, a family of pair with disjoint finite subsets of lambda, and if this family is large, then we can always find two different things in the disjoint family, such that when we evaluate the coloring from points from one set and the other, then they become 0. So this obviously tells you that in the ground model, you cannot have an homogeneous homogeneous set of size lambda, an homogeneous, well, one homogeneous, right? It cannot be, well, one homogeneous, because in particular, this A can be singletons, and then it means that, well, you will have 2 points when your coloring fails the one homogeneity. So this property 3 ensures that, well, the homogeneous set is in the ground model. But then, well, we want a failure of precaliber aleph 1, so we want this to be precaliber aleph 1. So this is where the D bars come in. So the D bars are like some types, okay? So they are they depend on alpha, on any alpha less than lambda, and they are functions, the alpha, from the finite subsets of alpha into omega. So this is like, defines like alpha types, okay? Countably many alpha types. So property 4 says that, well, if we have two homogeneous sets that are bounded by some alpha, and if they have the same alpha type, then their union is still one homogeneous. So this will ensure precalibrate LF1. So note that this property can be extended to any collection of one homogeneous sets. So if you have any collection of one homogeneous sets of any size, and if they are bounded by alpha, and if all of them are of the same type, then when you make the union of all of them, they will give you something that is one homogeneous. And this is what ensures precalibrate LF1. So remember that LF1 is smaller than lambda. So if we have LF1 many conditions in the forcing, so all of them are bounded by some alpha. So they are bounded by some alpha, and since they are uncountable, it means that we can shrink them to some uncountable of the same type, and then the union of all of them will be homogeneous. So in particular, that this will give you a centered subset of size LF1. So that's why this forcing has precalibrate LF1. So then under these conditions, what we call lambda type coloring, then we conclude that a lambda type coloring gives you a failure of precalibrate of MA on precalibrate LF1 with the obvious dense sets. So this is the main lemma. So now we want to preserve this. And the point is then that lambda 2 Naster posets will preserve lambda type colorings. This is the theorem that ensures the main result. Sorry, Professor Fucino, how much time do I have?
You have something like 6 minutes.
Okay. Now, I will try to do this proof quickly. It's a very short proof, actually, and it's a very standard argument. So the point is that, well, we had 4 properties for lambda type colorings, but only one of them is not absolute. All their properties are absolute because talk about finite things, but the only one that is not absolute is this one, which says that, well, that any this joint family of finite subsets of size and the family of size lambda, you can find 2 things where colorings are 0. So we have just to preserve the theory property, and that will be all. And the lambda Naster property will be to do this. So then we want to force number 3, preserve property number 3. So assume that P is lambda 2 Naster, P is a condition in P, and P forces that, well, we have something of size, some disjoint family of size lambda as in the property 3, as we assume in property 3. So then we try to decide each of the A alphas because, well, they are finite things, they can be decided. So for each alpha, we find a P alpha is stronger than P and some decision that we call B alpha. Then this gives us a lot of conditions. So since the forcing is lambda 2 Naster, this means that there is some large subset of lambda such that the P alphas indexed by this large lambda is to linked. They are linked. And this ensures then that the family of B alphas will be disjoint. So the family of B alphas will satisfy this property 3. So then we can find 2 different B alphas when the colorings become 0. Sorry, typo here, this should be eta. So the colorings become 0 here, but then for this particular alpha and beta, well, we know that this set is linked, so they are compatible. So there is a common stronger condition Q, and this says that A dot alpha is B alpha and A dot beta is B beta, and well, that these 2 sets are what we wanted because they have the property from the ground model. So then that's all. Okay, so thanks to this, then we can preserve the failure of the precalibrate LF1 property. So now how to produce it? Actually, well, this is produced in the obvious way. You just construct a forcing which is a finite approximation of the C and the D alphas that you want. You just force with a finite approximation, and this will give you something that is precalibrate LF1. So then you just have to put, instead of, well, starting with all the coins, you first start with this forcing, then add a lot of coins, and then do the rest. And then this will ensure that the iteration do what you want. Okay. So now to close this up. So we achieved our objective, but of course I was not like precise enough of what happens to the rest, meaning to P and to the cardinal Saint-Gihon's diagram. So then at this point, actually what we know is that, well, we have the result for the MK numbers, as I mentioned in the proofs. We can separate only the left side of Chihon's diagram and force that P is B. Okay, P actually is forced like quite large. But then with the method for forcing Chihon's maximum without large cardinals, then we can intersect with many models. And we can preserve property 1. So property 1 is not damaged after intersected with models, but P is modified. And actually what we get is that P can be H and G, the distributivity number and the graph-wise density number. And well, they will be thrown below additivity of none. So in this sense, we can separate P and the other stuff too. But then in addition, we can also, well, I will not go into details here, but the point is that if we have the forcing doing something, and if we make the product of this forcing with the sequences of mu of size less than mu, then in addition, you can separate P and H. And even, well, you can separate P and G, meaning that you can separate actually more values, not just P, but also separate P and H. I mean, in this equality, you can split here. P can be different from H. So this forms part, as I mentioned at the very start, from a larger setting, trying to separate all of this. So these are like a lot of classical cardinal invariants of the continuum. The Chihon's maximum, well, is done, like all the cardinals in Chihon's diagram can be separated. So then what I have been talking today is about this part, about the M numbers, about P, H, and G, that we can force them below the additivity of none and separate many of them. Also, more recently, we also separated S and R from this framework. So then it remains like to separate more stuff like H and G or E or the difficult stuff that is here, the almost disjoint number U or I, which is, well, more difficult challenges. Okay, so I leave it here for today. Thank you very much for your attention and for attending.
Okay, thank you very much. So are there any questions or comment? Okay, Miguel has raised, sorry, I saw Miguel fast, but Miguel Antonio Cardona Montoya has a question. No, that's just a, no, is there any question? Let me see, it's rather difficult to find people raising hand.
I have a question.
Yeah, please.
Yes.
I don't know how to raise hands. Sorry about that.
Yeah, okay.
Can you force M omega bigger than additivity null? Do you know that?
Yes. Even M omega can be forced. M omega can even be forced larger than. Can be even be forced larger than the covering of null.
Oh, okay. What is the model for that?
You just add precaliberal F1 things. The thing is that
I see. Okay.
Yeah, the precaliberal F1 doesn't add random reals.
Oh, okay. Thanks.
Yes, and I think even you have that with that covering of Sn is also, you can force with the same thing, covering of Sn below n omega. And
the other question is, I mean, you separated a lot, but in the final model, you still had that H and G were the same. Can you separate H and G in any way in these models where you separate many cardinals?
No, we don't know how to separate H and G in this context. I guess still at this point, we have no idea. Maybe Martin, who I think is here, could say more if he knows. No. Okay, he says no. He doesn't know. So yeah, we don't know.
Okay, thanks. That's all for the moment.
Okay.
Any other questions? Yeah, so you separated this lower part of the diagram and then separated Chihon's diagram cardinal numbers apart. But how is the different possibilities of making them different? Is there still certain flexibility, or it is just one way to put this Chihon's diagram above the separation of Martin's axiom type numbers?
Yeah, of course. Well, there are many open questions in this direction. Like, well, the restrictions that we have so far, if we want to talk about the restrictions first, because everything is in finite superiteration context, we are attached to this, right? Like this has to happen in this context, right? Also, well, for this number G or M or P or G, in order to separate everything, everything must fall below additivity of null. So it's some other restriction. And well, and finally, well, I mentioned that S and R could be separated. So we are restricted to have S less than B and D less than R. Of course, it could be possible that S could be larger than B, right? Like this is consistent. Yeah, when incorporating S, yes, like it's very difficult to increase S while not adding dominating reals. So this is like a very hard restriction. And well, this is just to mention some, but of course on the Chihon's diagram itself, like there are many possibilities there, and only for Chihon's diagram, even when extending like this, we only know like 2 possibilities. Right? But of course, there are much more than that for Chihon's maximum.
Let's see. Any other question? No. May make a very stupid remark. So stupid that I almost do not dare to say, but I think the Polish name is Knasta and not Nasta. Because there are several Polish participants, I can just ask them if my theory is correct, but I think...
yes, it's Knaster.
Yeah, okay.
Yeah, I will have it in mind. Thank you.
Yeah. I think Chris pronounced it correctly. Yeah. Chris,
you don't have to know that. You don't have to know that.
Yeah, right. Exactly. Yeah.